Hello, my name is Biphasic, and my goal in this four-part lecture is to provide a simple, not too technical introduction to the technical concepts underlying neuromodulation devices, really to give people of diverse backgrounds an appreciation for the kind of terminology that gets thrown around in neuromodulation technology, things like electrodes and pulse width, and so on. And so I will be explaining this terminology and its significance in as simple a way as I can, starting with part one: electrodes, current flow density, electric field, tissue resistivity, and impedance. So we first want to understand that when we have a stimulator, that stimulator will have wires that go and touch the body. And the stimulator will push out current through the wires and therefore through the body. And so we have current flow. Now, there is very specific points where current can cross into or out of the body, and only at those points. And those points are called electrodes. So electrodes is the point where current exits the device, including the wires, and enters the body, or enters the device, so it's being drawn from the body. And so if you think about it, you can see that you must always have two electrodes. One is the anode. The anode is where current is entering the body from the device. And then you have an electrode called the cathode, which is the other electrode, which is drawing current out of the body. So that is the anode electrode and the cathode electrode. And when we move these electrodes around, we move where current flows through the body, right? So this is the simple principle of where we place the electrodes will influence what part of the body we stimulate, because to first approximation, current will simply flow from one electrode, the anode, to the other, the cathode, and stimulate the parts of the body that are in between. We also get the appreciation that when we talk about stimulation, there is sort of one current. There's the current that exits from the device, travels down the wire to the anode. That same current must enter the body, and then it is sucked up by the cathode and is drawn back. And so when we talk about stimulation, we'll often talk about stimulation current or voltage as far as intensity. That current will be specified in units of amps or milliamps, which are 1,000th of an amp. So for example, I might stimulate with 2 milliamps. And it's 2 milliamps at the device, it's 2 milliamps at the anode, it's 2 milliamps in the body, it's 2 milliamps at the cathode. The point is it's one current that we can talk about because of the notion that we have this conservation of current as we go along the loop. But when current enters the body, it doesn't flow in a straight line from the anode to the cathode, right? That would be a straight line straight down. The current tends to enter the body, and just like it would if it entered a salty bathtub, it tends to spread out, travel in different pathways, eventually start to come together to coalesce, and then be collected on the cathode. So while as in a wire, current might be flowing just in a straight line, in the body, which is a salty bath, the current is actually diffused around. And so instead of talking about current, you will see the term called current density. So how do we think about current density? You get a good sense of what current density is by its units, which is current per area. For example, milliamps per centimeter squared. I want you to imagine that there's a window, and let's say that window is 1 centimeter by 1 centimeter, so it's simply 1 centimeter squared. And through that window, over the net amount of the window, there's 1 milliamp flowing through. It's flowing through different parts of the window, but over the entire window, there's 1 milliamp flowing through. And therefore, we will say that that window has a current density of 1 milliamp per centimeter squared. If we double the current, it would be 2 milliamp per centimeter squared. If we made that window twice as big, but kept the current the same, then the current density would go down. So that is a simple calculation of current density. And there's the calculation. And when we describe current flow through the body, we might often talk about current density. So think about a bunch of little windows sprinkled throughout the body. All these windows are the same size, and there's current flowing through them. Now, the amount of current that flows through each window is not the same. Some windows near the electrodes might have a lot of current flowing through them, while other windows farther away might have less current. And so therefore we will have windows with more current density, more current per window, and we will have windows with less current density. And typically, windows near the electrodes will have higher current density because the current doesn't have a chance to split up yet. You can also see that the current density has a direction, right? So it's not just that it's flowing through the window, but what is the direction you can imagine that window is facing, or how is it crossing through the window as it crosses through? So when we talk about current density, we don't just talk about how big it is at each location, we can also talk about the direction that it's flowing in. So current density has a magnitude, a size, and it has a direction. You will sometimes hear the term electric field, which is in units of volts per meter, describing the current flow pattern through the tissue. Current density and electric field are very much related quantities. Often they look very much the same. When they don't look the same, it's because they are related by the resistivity of the tissue, a concept I'll come to later. But for now, just need to understand that just like current density is a bunch of little windows with arrows, electric field is similarly a bunch of windows distributed through the body with arrows indicating the amount flowing and the direction that it's flowing in. Now, instead of windows and little arrows, we will often represent this in terms of colors or false color maps. So what we would say is that areas with a lot of current density or a lot of electric field will get the color red. Those windows will get the color red. Areas with low current density or not a lot of electric field would get the color blue. Let's say, again, this is an arbitrary scale, but these are the colors we assign, and green is in the middle. So now what you're looking at is a lead, maybe a DBS lead, maybe an SES lead. Those wires, the lines represent where the current is flowing through in the tissue, and the false color is how much current density is in each little window. And you can see there's more current density near the electrodes, right? And as you move away from the electrodes, the current density drops. And how much it drops, how quickly, will depend on different things, like how big the lead is. So that's what these false color pictures of current density or electric field mean. Now, the body is not exactly like a salty bath. It's built of different things, things like bone, for example, which has a high resistance. It doesn't easily pass current through it. It might also be made of cerebral spinal fluid, which has a very low resistance. It's very easy for current to flow through it, and tissues in the middle, like gray matter and white matter. So every tissue in the body has a resistance, or more technically what's called a resistivity, which has units of ohms meter. Skull has a high resistivity. Cerebral spinal fluid has a very low resistivity. And so now we have a cartoon where we have our anode, where current is entering the body, and the cathode, where current is exiting the body. And now we're drawing how current is flowing through. And generally speaking, current will try to find the overall path of least resistance. And what that means is that current will favor paths of low resistivity. So we have now CSF surrounding skull. Most of the current will wrap around the skull. Will try to avoid it. And so we see that the pattern that we get is not just a function of where we place the electrodes, but it's also very much dependent on the anatomy and the resistivity of different tissues. Now, this current flow pattern can get more and more complicated. So here's another situation. We have our anode and a cathode. Let's say we have a high resistivity barrier, a little square brain with CSF around it. How will the current flow from the anode to the cathode? When it crosses through the high resistivity tissue, it actually ends up getting spread out a little bit. This is just a cartoon notion, but this could happen because it's very hard for it to get through, and so it spreads out to try to make that easier. Then it crosses into the cerebral spinal fluid, the CSF. This is a superhighway. Now it's flying around. The gray and white matter is relative to the CSF, rather resistive, so most of the current will prefer to avoid it. Now we'll start to travel upward now towards the cathode, and then it will be removed. And again, this is just a cartoon version, but what I want you to imagine is how this can get quickly rather complicated when you start dealing with real three-dimensional anatomy and lots of different tissue types. And that is why computational models of current flow are developed. These are models which represent the anatomy and the different tissue types, like bone, like CSF, like white matter, and like gray matter. And once that is represented, they can predict the current density, the current flow pattern through these different tissues, and again, represent that as a false color map. And the reason we need these models is because it actually gets hard to guess what will happen as the tissues get more and more complicated, and you'll hear different terms like CAD-derived, image-derived, finite element, numerical solutions. All these are terms that are used in this field of computational models, but all computational models of current flow start with the representation of the anatomy and end with a picture that we've described as a false color map of where which parts are getting more electricity, more current density, and which are getting less. Now, we can measure the resistance, which will often be called the impedance, between the two electrodes. This is not a measurement of the resistivity or resistance of any given tissue, but the resistance that the overall device is seeing between an anode and a cathode. And there are technical reasons why we might call it a resistance or impedance, but as far as what you would see reported by device, these things are usually conflated, and you just get one number, like 1 or 3 or 100 or 1 kilo ohm, 1000 ohm, and the units are ohms. So ohms would be the units of resistance. And so often devices will report resistance or impedance. This needs to be understood as a measure of the overall resistance to current flow. It includes everything that exists between the anode and the cathode. It is very sensitive to conditions right around the electrode. That's where everything has to flow through there, if you can imagine. So any kind of issues around there are going to be really important. So for example, if the cathode has been somehow clogged up through an encapsulation layer or even broken, that would then result in an overall increase in the resistance for the path. And then the device would report, hey, I'm experiencing a really high resistance or a really high impedance, and then that issue would have to be addressed, usually by looking at what's going on near the electrodes themselves. Okay, moving on now to the second part, and simply introducing the concepts of membrane polarization. You'll hear about neuronal polarization, action potential threshold, which I'm just going to explain in the context of neuromodulation, and also a related concept of volume of tissue activated, which is used conceptually in neuromodulation. So the brain is made out of different neurons, and they have complicated shapes with their somas and their dendrites and their axons, but the key feature is that each cell is defined by a membrane. And so we have essentially an interior pocket of conductive fluid, an insulating layer that forms the membrane, and then the outside pocket. So that necessarily has to be the case. So I want to think now, instead of this complicated structure, I want to present the cell as just, let's imagine it's a tube. All right, but I want you to realize that this tube is really the shell. The shell is the membrane. The inside is the inside of the neuron. It's filled with whatever neurons are filled with on the inside. And the outside is the extracellular space, right, which is also filled with fluid and ions. And the membrane only represents the sheath that surrounds it. I now want to expose that tube to current flow. Why is it exposed to current flow? Well, maybe there's an anode on one side and a cathode on the other, and we are pushing current through this bathtub or through the body, and as it passes through, it's going to pass along the neuron. So we now have a current density, the green arrows, or an electric field generated outside the neuron because the stimulation is on. A lot of the current will flow around the neuron, but some of it will pass through the neuron. Now, to pass through the neuron, it has to pass from the outside in, flow along the inside, and then pass from the inside out. As I've shown you before, current can't disappear. And so we have to have this notion of conservation of current. So if it flows in, it must flow out somewhere. And you can see that therefore we have a situation where one side is crossing, the current is crossing from the outside to the inside of the cell. And on the other side of the cell, the current is crossing from the inside to the outside of the cell. And it's important to distinguish these two features, the current flowing in on one end and the current flowing out on the other end. Because where current flows into the cell, it will do something called hyperpolarization. And where current flows out of the cell, this tube, it will do something called depolarization. Hyperpolarization means that the inside becomes more negative compared to the outside. Depolarization on the other side means that the inside becomes more positive relative to the outside. So one end is hyperpolarized and one is depolarized. Why are they being polarized in opposite directions? Because the current flows in the opposite direction. It's flowing in versus flowing out. And just referring to basic circuit theory or Ohm's law, we can see an analogy here where this resistance, these resistors I'm showing are now the two membranes on either end. And we have the current flowing in the same direction, but in one case it's going outside to in, in the other case it's going inside to out. And so from the perspective of the inside of the cell, and that is how we define membrane potential, it's just defined conventionally from the inside, you can see that on the left side, the inside becomes more negative compared to the outside, while on the other side, the inside becomes more positive. So we get a membrane polarization, right? We started with current flowing outside the cell. Some of that current crossed into the cell, and where it crossed into the cell, it polarized the cell in this kind of seesaw fashion. And I've shown that for a tube, but this idea applies for all neurons, all realistically shaped neurons. I mean, this is still a drawing, but you get the idea. You have now one side of the cell blue that is being hyperpolarized. That's where current is flowing into the cell. And we have the other side of the cell, including the soma and the axon, where the cell is being depolarized. That's where current is flowing out of the cell. So hyperpolarization, depolarization as an inevitable consequence of generating a current density, which is an inevitable consequence of passing current out of our device. And we have computer simulations, again, that can predict exactly how much polarization you'll see in which part of the neuron, but they will generally respect this kind of cartoon level intuition that I've shown you here. Okay, how much does matter? Now, I'm going to be walking through some examples. These are, numerically, these are made up examples. These are not at all realistic. The point more is to use simple numbers to try to give us a little bit of intuition about what's going on here and how to interpret the amount of polarization. Let's say hypothetically we have a current density of 1 milliamp per meter squared, or an electric field of 1 volt per meter squared, volt per meter. Again, these are made up numbers. All right. And I want you to assume that this current is flowing, some of it will flow through the cell, and the amount that flows into the cell on the left side will hyperpolarize it by 20 millivolts. So that's what I mean by negative 20 millivolt. And current that is exiting the cell on the other end will depolarize it by 20 millivolts. Again, made up numbers, okay? But and we understand why there's a seesaw effect here on the two sides. Now the cells don't start at 0 millivolt. The neurons don't start at 0 millivolts. They have what's called a resting membrane potential. Let's put that resting membrane potential at minus 70. So that's our baseline point. Simplistically, we would say if we start at minus 70, resting, and we apply a current density, which causes current to flow through the membrane, that hyperpolarizes it by 20 millivolt, we will go from minus 70 millivolts to minus 90 millivolt. On the other end, where current is flowing exiting, right? And so we have a 20 millivolt depolarizing influence. If we started at minus 70 millivolts and we add 20 millivolts to that, then we will get to minus 50 millivolts. Now, is this a zero-sum game, right? Because one end went down 20, the other end went up 20, so what, does it all cancel out? And the answer is no, because the cells generate action potentials. On the side of the cell, where we went from minus 70 to minus 50, an action potential is generated, an intense regenerative process that is built into the neuron that causes a massive and transient deflection in the membrane potential called an action potential, and that has many, many consequences to it. This will happen on the side, simplistically, that is depolarized. And so that's why it's not a zero-sum game, because in this case, it's not zero. Yes, one side may not fire an action potential, but the other one does, and therefore the neuron as a whole will have generated an action potential. If we apply additional stimuli, pop, 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 we can actually generate an action potential with each stimuli. And an important idea is, once we stimulate intensely enough to make an action potential, we don't make bigger action potentials, right? If we go from minus 70 to minus 50, we get an action potential, which is whatever big it is, and that size is set by the cell. If we stimulate and go from minus 70 to minus 40 and trigger an action potential, we'll get the same size action potential because the size of the action potential is really governed by the cell's own explosive regenerative property. And the only thing that the stimulation is doing to a first approximation is giving it that little kick. And so the minimum amount of current you need, we'll call it the threshold, right? That's how much current you need to just make it fire an action potential. If we stimulate harder than that, we could call it super threshold, but it's still threshold as far as just generating an action potential. So not zero sum because of the fact that these cells generate action potentials, and that is the primary consequence of neuromodulation or electrical stimulation, the driving of action potentials as a result of the generation of a current density / electric field, leading to a sufficient polarization to get these cells to threshold. Now, if we decrease the intensity, let's say we decreased it here, it's a factor of 10, again, arbitrary, so we turn down the stimulator by a factor of 10, we get a tenth of the current density, a tenth of the electric field, and a tenth of the polarization. Well, now we're taking the cell from minus 70 to minus 68. It's not enough to get an action potential because that's not at the cell's, whatever its cell's threshold is. So we can see that if we stimulate too weakly, we do not get an action potential because all these things are muted. All these things are scaled down. Okay. Now let's combine a couple of these ideas. We have now the anode and we have the cathode. And we talked before how there is a higher current density near the electrodes and a lower current density farther away. And you can interchange electric field if you prefer with that. There's more packing of current density near the electrodes, and as you move farther and farther away, that decreases. So let's imagine we have now a region of near the electrodes of dark gray of 1 amp per meter squared and a region farther away of 0.1 amp per meter squared. This drop is simply a consequence of distance, right? There's still one stimulation coming out of the device, but the drop happens as a consequence of distance. Now let's populate some neurons in there. Some neurons are going to have to be near the anode and the cathode. Some are going to happen to be far away. And what will happen? Well, the neurons that happen to be near the anode and the cathode will polarize enough to fire an action potential, because the calculations we did before, that's enough, right? Arbitrary numbers. The neurons that are farther away from the anode and cathode are exposed to a lower electric field or lower current density, and by virtue of that, by virtue of their distance, they will not polarize to fire an action potential. So it's all action potential for the greens and no action potential for the purple. And people will sometimes talk about volume of tissue activated to represent this idea. So now we'll say, okay, the green regions, this is the space, the volume in which neurons will fire, in which they will be activated. And therefore everything outside of it is not activated, is not inside the volume of the tissue that is activated. That is one way to represent what is happening. Now, a nuance to that is these cells, right? There's axons that are coming to or from these cells. You can imagine a situation where you stimulate a region, I'm going to call that the primary target, but those neurons have axons that then project to another target, and therefore we'll get activation in the secondary target. It's why people are very interested, not just in which neurons are being stimulated, but also which axons are being stimulated, and it's then we can track where those axons go, and we can identify sort of secondary targets as well. And by the way, this will also happen for axons arriving at the primary target. So it's an additional conceptual step, but it turns out that it's one that's very important in areas where, like, they're called circuit therapeutics, or where tractography is being used to inform neuromodulation. However, none of that additional layer takes away from the concepts that have just gone through so far. It still starts with a current density and a polarization and an action potential. Okay, moving on to part 3, and again, I'm really going to be focusing here on just giving you a very quick and intuitive introduction to concepts that come up in neuromodulation, technical jargon, words that are important to understand, not just if you're an engineer, but if you're a scientist or a clinician working in the space. Words like waveform, intensity, pulse duration, biphasic, bipolar. What do these terms mean? So we had this initial example before where we're applying 1 milliamp total of current. And again, I want to keep saying arbitrary numbers here. And we get a higher current density near the electrode and a lower current density farther away. And we went through an example where that then leads to a volume of tissue activated that looks something like this. The nearer ones happen to fire. If we now increase the current, right? So we go from 1 milliamp to 10 milliamps. What happens is you get more current density everywhere. If you do 10 times the current, you will actually get 10 times the current density everywhere. So that means that near the electrodes, we went from 1 amp per meter squared to 10 amp per meter squared. And farther away from the electrodes, we went from 0.1 amp per meter squared to 1 amp per meter squared. Now, what does this mean for the volume of tissue? And again, there's a nice scaling factor here. It's very linear or scaly, if you want. What happens? We now have a new volume of tissue activated. Now, both the neurons close to the electrodes and the neurons far away are activated. And remember, the ones near it are not going to generate a 10 times bigger action potential. Once you go, you go. And so what's really happened here is, as I've shown you, is that you'll tend to activate things near the electrodes, right, near your anode or near your cathode. But what near means will change, because as you increase the stimulus intensity, you will activate a bigger and bigger region. And again, it's action potential all or none, not bigger action potential, as we go to higher intensity. But an additional further concept is that we don't just need to think about intensity, which we're talking about in terms of amps or milliamps, or you could talk about in terms of volts. You don't just need to talk about intensity, but you also need to talk about pulse duration. When we apply stimulation, we have how strong it is, but also how long it's on for. It's not on forever. And so when we apply pulse stimulation, tick, 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 every one of those ticks has an intensity, but it also has the time that it is on. And that time would be given in seconds, or in neuromodulation, really a fraction of a second. So we'll talk about 1,000th of a second, which is 1 millisecond, or even less than that, 1,000,000th of a second, so microseconds. We might say it's a 1 millisecond pulse, or a 100 microsecond pulse. But the seconds refers to how long that pulse is on for. And it turns out that the intensity and the duration both matter in determining what happens. And this is because of a concept called the strength duration curve. And I only need to explain it here in a sort of cartoony way. When we have long pulses, right, which is sort of going on the right, where you see 100 microseconds, 200 microseconds, we have a certain intensity that we need to produce action potentials. Let's call that 1. That's where that horizontal dashed line is, right? So at 200 microseconds, we need 1 milliamp. At 400 microseconds, we need 1 milliamp. But as duration gets shorter, as we go, let's say, from 100 to 50, and from 50 to 10, we discover that we need much more intensity to make the same neurons fire. All right, so at a long enough length, it doesn't seem to matter. But once we get to shorter pulse widths, which are actually the pulse widths we use in neuromodulation, there's this trade-off where the shorter the pulse, the more amplitude you need to produce activation. And so that is what this strength duration curve is. On the x-axis is the duration of the pulse, and on the y-axis is the intensity you need at that duration to produce an action potential. What is this? So it's that strength duration curve. And there's, by the way, a minimum. So once you cross a certain amount, it doesn't drop anymore, right? And that lowest amount is called the Rio base. You'll hear terms called the chronaxy, which is the pulse width at which it doubles. But for the purposes here, the only thing to understand is as you start to go to shorter pulses, you need more current to produce action potentials. And in fact, very short pulses as a result don't work. I mentioned that in neuromodulation, you won't see long pulses. You'll see shorter pulses on around 100 microseconds, but you won't see 1 microsecond pulses, because then that's like too much. That's going off in the end. Let's think about that in terms of the picture I've been showing you. We now have 10 milliamps of stimulation, but I've now specified that this is with a 1 millisecond pulse duration. So it's 10 milliseconds lasting for 1 millisecond, and let's say this is the volume of tissue activation that we got. Now, if we decrease the duration from 1 millisecond to 0.1 millisecond, but we're keeping the amplitude the same, the volume tissue activated will shrink, right? Because the ones on the outskirts, right? The ones on the outskirts are no longer exposed to a strong enough current density at that pulse width to fire. So same pulse intensity, but different width. And so this is why it is so important to consider both intensity, pulse size, and pulse duration. I've been saying pulse width, but pulse width / pulse duration, both matter. More intensity, more activation, more duration, more activation, less of either, you start to lose. All right. Now I want to talk about pulse polarity. People talk about, oh, it's plus 1 milliamp, it's minus 1 milliamp. What exactly does that mean, right? And what does it mean when people say biphasic, right? So biphasic means that the current flows one way and then it flows the other way. Imagine you have an anode and a cathode. Remember, the anode is where current is entering the body, and the cathode is where it's being collected. So the current flows from the anode to the cathode. Now, I suddenly reverse gears. So now the electrode on the bottom, which was previously the cathode, becomes the anode, and the anode on top becomes the cathode. So both electrodes are still active, but what's reversed is the direction that the current is flowing in. This is what's meant by biphasic stimulation. There are in fact two pulses, and they can be very similar except for a reversal in direction. So in a sense, they both are at some level of milliamps, but the milliamps are flowing in an opposite direction. And this is not an esoteric idea. This is basically applicable to almost all neuromodulation. So that's what biphasic stimulation means. Now, the question can come up then, which one is the anode and which one is the cathode? Right? Because in the first time, like that first pulse, when the current was flowing down, the top one was the anode. But in the second pulse, when the current was flowing up, the bottom one was the anode. So one's the anode, then the other one's the anode. So that seems a bit confusing. And if I want to talk about positive or negative current flow, again, how do I address that issue? And the simple way to do that is you just identify a reference. So I'm going to say that electrode 1 is like my electrode of interest. That's the one I'm going to focus on. And the electrode 2 is like the chaser. So now when I say 1 milliamp, I mean 1 milliamp from electrode 1 to electrode 2. And when I say minus 1 milliamp, so just strange thing to say, right? Minus 1. What I mean is electrode 1 is minus 1 milliamp, which means it's sucking up current. And therefore electrode 2 is at plus 1 milliamp. But and you're going to say, well, could you have picked the bottom one? You could have too. But when we talk about polarity, when I say I applied 1 milliamp and then I applied minus 1 milliamp, I have to tell you which electrode I'm referring to, because in fact both are having sort of this double role if you've been following along. So we simply have to define an electrode that is sort of the one we're going to be defining the polarity in terms of. Often we will have an electrode that we consider more important. We'll call it the active electrode, and another electrode that we might call the return. Now, active and return, these are terms of convenience, but let's say one electrode is right near the brain region I'm really interested in. I'm going to call that the active. The return electrode is near a brain region I'm not interested in, so I'm going to call that the return. And now I'm going to start defining polarity, as in plus 1 milliamp or minus 1 milliamp, in terms of the active or in terms of the return electrode. Now again, this may seem a bit of an esoteric concept, but it's just something I think you need to keep in mind, because maybe it will come up in the process of describing a particular neuromodulation approach. But what is certainly true is that almost all neuromodulation and all invasive neuromodulation, with very few exceptions, will use a biphasic stimulation so that each electrode is going right? Each electrode is doing a push-pull, right? Or a pull-push, right? So that's what we call biphasic. And you will get these terms called the anodic phase or the cathodic phase. And I want to imagine that we're talking now from the perspective of one electrode. And that one electrode first acted like an anode. There was positive current coming out of it. And then that same electrode was later acting like a cathode, where current was going into it. Where it was acting like an anode, we will call that the anodic phase pulse. And where it was acting like a cathode, we will call that the cathodic phase pulse. Now, if you've been following, you realize that if one electrode is in anodic phase, the other one must be at the cathodic phase, right? So this terminology will always be about one electrode, right? And we can alternatively say, actually, we're going to do cathodic phase first and then anodic phase. What that means is that from the perspective of one electrode, first it will act like a cathode. It will draw current in. So we'll talk about negative current, right? And then later, it will spit current out and act like an anode. So it has a cathodic phase first and then an anodic. So when people talk about biphasic pulses, they will talk about anodic phase and they will talk about cathodic phase. This really needs to be defined in terms of one electrode. And all it means is, am I acting like an anode at this time or am I acting like a cathode at this time? Sometimes people will talk about anodic and cathodal stimulation by just referring to the first pulse, which is maybe a bit confusing when you have sort of biphasic stimulation, but they'll say that the top example is anodic stimulation, while the bottom pulse is cathodic stimulation. Other times what they'll do is they'll look at each of the phases and they'll say which one they think is more important. So even in the top case, they might say, oh, that was cathodic stimulation, because for whatever reason, I really want to focus on the cathodic term. Now we really are getting into the weeds, but understanding what the terms anodic and cathodic phase means will at least allow you to start to follow that discussion as you get into it. So now we can talk about, an active electrode and a return electrode. These are arbitrary terms. The active electrode is near the targeted region. And now let's imagine that we're doing biphasic stimulation. All right. We lead with the cathodic phase. That means that the active electrode is first negative. It is drawing current in. Let's say that lasts for 1 millisecond. And then a little while later, we turn that off. We switch to the anodic phase, which means the active electrode is now pushing current in. Again, let's say for 1 millisecond as well. And so now we have a description of a more realistic description of a stimulation process where we talk about both intensity and we talk about duration, and we are careful to define the intensity and therefore the phases relative to one electrode. And it turns out that whether you go cathodic phase first or anodic phase first may have a big difference. So I'm trying to show you here, and again, this is a cartoon only, is it's possible that we have a volume of tissue activated at the top. Those neurons go, but the neurons at the bottom don't. And the only difference between the top and the bottom is the top was cathodic phase first, followed by anodic phase. Well, the bottom, if you think about it, was anodic phase first, followed by cathodic phase. So again, this is a difference with a distinction. If we lead with cathodic phase or lead with anodic phase, it may have an influence on the volume of tissue activated. All right. Some other terminology, right, that gets thrown around. Monopolar stimulation. Monopolar is not monophasic. Okay, monophasic is the opposite of biphasic. Biphasic is when the waveform switches. Monophasic is when the waveform never switches, right? Which doesn't happen with invasive technology. All invasive is biphasic. Monopolar stimulation refers to the electrode shape itself or where it's placed. When we have an active electrode that is much nearer the target, or perhaps even smaller, right? Or smaller and nearer the target, while the other electrode is farther away and larger, or farther away and larger, we will call that monopolar stimulation. Contrast that with bipolar stimulation, where the two electrodes, right, are roughly the same size, right, and roughly the same distance from the target. So in the bottom case, electrode 1 and 2 are kind of mirror images of one another, right? That electrode configuration will be called bipolar. Well, in the top case, there's this asymmetry with sort of one dominant player. So again, monopolar and bipolar do not refer to the waveform. It's not the phasic thing. It refers to the configuration of the electrodes. And so this gets us into sort of quickly describing how we set up these electrodes. Imagine now you have a lead with 4 contacts. We're going to activate some, right? And we're going to send current in through some, collect current through others, but the others will remain inactive. So for example, maybe I'll use my electrode 2 as the anode, and I'll use my electrode 3 as the cathode, so current will flow from one to the other. Electrode 1, and sorry, should be labeled electrode 4 in the bottom, they're out of the picture. They might as well not being used at all. So the perspective of current flow, the top and bottom electrodes don't matter in this case. So this is bipolar stimulation, probably, right? There's two electrodes that seem to be playing an equal role, right? And in this case, I'm showing you what would be called maybe the anodic phase relative to electrode 2. I know it's getting a bit complicated with these concepts. Now, let's say I go from electrode 2 to the bottom of electrode, incorrectly labeled electrode 3, right? I've now changed which electrodes I'm using. As a result, the current flow through the tissue will change. The pattern will change. So these two situations are not equivalent, even though they're both, using two bipoles. In one case, you could say they're proximal, they're nearby. In another case, I might say, oh, that's a more distal bipolar arrangement. So now you see this further terminology coming in. Now, up to now, I've always shown you one anode and one cathode. It does not have to be that way. You could have one anode and two cathodes. Imagine that the center electrode is injecting 1 milliamp, and each of the other ones are collecting half a milliamp. So the total current is still 0, 1 milliamp in, half and half out, but it's being distributed in a different way. Such configurations will also exist. I just want to flag up to your attention. They will get their own names: tripolar, guarded tripolar, guarded cathode, right? Now you know they're sort of combining concepts of montage and phase and leading phase. So you'll see these terms come up, but I think based on what I've described to you today, you'll at least be able to trace back and decompose what those terms mean. Sometimes, like with a IPG, the exterior of the device itself is used as an electrode. So they'll call it, that's the can return, right? And so now you'll have one electrode on the lead, and the current is entering there, and it's traveling all the way through the body and being collected by the can itself. And in those situations, you might also use the term monopolar, because there's really one small electrode that is active and a distant, larger electrode that we consider less important. So you see an example of how the term monopolar is used. Now, as I keep emphasizing, for invasive devices, stimulation is always applied in pairs. Each electrode is like, right? But the pairs are repeated. This is where frequency comes in. So I have an electrode, it pushes current in, sucks it back out. A little while later, which we will call the pulse period, the electrode once again pushes current in and pushes current out. So the time between pairs will be called the pulse period. Let's say that pulse period is 1 millisecond. And then that's repeated again and again. So every millisecond we have a pair. That will also be described as 1 kilohertz stimulation, 1,000 hertz, because 1,000 times per second we have a pair. Simpler math, imagine there's 1 second between each couplet, right? We will now say that we're stimulating at 1 hertz. Once per second, we have a couplet. Now, if you're thinking about it, you'll realize that there's actually double the amount of pulses, right? So if we're doing a couplet every second, then in fact, every second there are 2 pulses, one going in and out. But in neuromodulation, these couplets are so interrelated. The stimulation is so inherently biphasic, and these couplets always run together. For the purpose of talking about frequency, we group them together. And so again, when you hear 100 hertz, it means 100 of these couplets are coming per second. You'll sometimes hear the term interphase. Interphase is the time between couplets. They tend to ride hot one on top of the other, but there could be a little bit of a gap, right? So you'll hear on the one hand, pulse duration, that's how long the pulse is. You will hear the pulse period or the frequency, the time between couplets, and then you will hear the interphase time, which is the time between phases. And hopefully, those terms are starting to make sense as I've described, as I've sort of built up this particular story. And again, the frequency is the inverse of the pulse period, right? So that 1 millisecond, it should really be 1 millisecond pulse period, right? Leads to, let's say, 1,000 hertz or 1 kilohertz. 1 second pulse period leads to 1 hertz. But there's a couplet. A couplet is counted as 1. And the reason the couplet comes as 1 is it's often understood that each couplet will produce 1 action potential. And there are different technical reasons for that, but essentially, if you are stimulating at 100 hertz, which is 100 couplets, you are expecting to generate action potentials at 100 hertz. Okay, if you're stimulating with a couplet 100 times per second, you will get an action potential 100 times per second. So not both phases produce an action potential. One phase is doing the action potential. The other phase is playing a separate role. It's not producing another action potential. So that is why when people talk about neuromodulation frequency, they really talk about the rate of couplets. Now we need to be a little bit more nuanced here. Some couplets look the same but sort of flipped, and some look a little different. So we have something called symmetric biphasic. Symmetric biphasic means that the couplets have the same amplitude and the same pulse duration, but it has to be reversed, right? So it's in and out. Asymmetric means that you have a couplet, but each side of that couplet doesn't have the same shape. They have a different amplitude and a different duration. So those are the examples I've shown you here. However, the total area must always be the same. All right, so from a safety perspective, we need to do something called charge balanced. What that means is that if you multiply the amplitude and the duration of the first pulse, and you multiply the amplitude and duration of the second pulse, those must be equal to each other, but of opposite sign. So in this case, you can see we have 1 millisecond and minus 1 milliamp. For the asymmetric pulse, I made the amplitude half, but then I had to make the duration double. So you'll hear the term charge balanced. What that means is that these shaded regions are always the same. If you hear charge balanced, they must be talking about biphasic pulses. They may be either symmetric or asymmetric. Okay, so that term comes up as well. And again, now you can think of all these things that, biphasic, again, is for a safety reason. You have, again, with biphasic, you must always have a cathodic phase. You must always have an anodic phase. And it's universally biphasic stimulation, almost universally when using pulses. Not because you're getting somehow double the stimulation, but because one of the pulses is playing cleanup duty to the other one from a safety perspective. Now, it turns out there's more nuance to pulse design. Monophasic, again, is not going to be used with an implanted device. But you can see here just random permutations. The bottom one is charge balanced, but biphasic, but you can see it's an asymmetric biphasic. In row C, you can even see that the pulses don't necessarily have to be squares. There's this sort of capacitive recovery on one pulse here. In D, you can see that the interpulse interval is being varied. And there is a lot of research on how you shape these couplets to produce different effects. These are not the same. They're not the same from the perspective of activation. They're not necessarily the same from the perspective of electrochemical safety. For the purpose of what I'm talking to you here today about, it's just important to understand that there are different compositions of what these couplets look like. Okay, so what's the big takeaway up to now? Stimulation dose is a very specific concept in neuromodulation. It is all the parameters that I've talked about so far. It's where the electrodes are. It's the waveform that we're playing into them, this pulse waveform. How fast are those pulses coming? They're coming in a couplet. How fast are those couplets coming? What is their frequency? In each couplet, did we start with an anodic phase first or a cathodic phase first, defined relative to one electrode? How big is the amplitude? And is the amplitude the same for both sides of that couplet? How wide is each pulse? So all these parameters that I've described to you so far is what's meant when people talk about neuromodulation dose. What is the dose of neuromodulation? It is all these parameters, and they are considered critical to be aware of when designing and when implementing neuromodulation. And what's interesting is two devices with the same dose are indistinguishable to the body. It doesn't matter that one is made by company A and it's red and one is made by company B and it's blue. As far as the energy that's delivered into the body, the electricity, two devices with the same dose are indistinguishable to the neurons, right? Because as far as the neurons are concerned, same electrodes, same frequencies, same pulse width. So that's an interesting idea. And conversely, if two devices provide a different dose, or if the same device is programmed one way and then another way to provide a different dose, they produce different effects. Another thing I want to mention is you'll see a lot of additional jargon to what I'm talking about. Pulse density, kilohertz waveform, burst waveforms. Those are important. They give you context on some aspect of like pulse density. Will explain how fast these pulses are coming one after the other. Kilohertz obviously suggests we're now moving to above 1,000 hertz. Couplet frequency. Burst has to do when the couplets come in bursts up, like where they're grouped out. And all that's wonderful, but I want to mention that just saying burst, it doesn't substitute the need to actually fully define dose. Just saying I did kilohertz doesn't mean that we shouldn't still fully define dose, because all aspects of dose matter. All right, one burst is not the same as another burst. One high density is not the same as another high density. So summary metrics are interesting. They're used good for paper titles and stuff, but they don't replace fully reporting dose. And we also now understand that each device can provide many doses. It's not that the device comes with one dose. Each device, the electrodes can be implanted in different locations. You have tons of knobs to fool around with. So each device must be implanted, and each device must be programmed. And what you're doing when you're doing that is you are setting the dose. And I like to use the term dose instructions. The dose instructions are the label that comes with the device, the experience of the rep, the instructions that are given to the patient. All that dose instructions are the instructions of how to adjust dose. And they are very important to keep in mind, right? Because the dose instructions will govern what dose we end up with. And so they're actually as important for reproducibility as the device itself. And then a final point here is that dose matters, but it doesn't strictly determine outcome. And the reason is we have different anatomy. So the same dose on different anatomy will lead to different current flow pattern. And we have different physiology and physiological states. So the neurons are not all the same, and their state is not always the same. And so dose is like really, really paramount. It's what we control. It's what we prescribe. We must be aware of it. But setting a dose does not guarantee a specific outcome in a specific patient in a specific time because of these other factors. And that's a bigger talk. I just want to end part 4 here, 3 things to change everything, right? I got to put twists on things a little bit. And I'm only going to be introducing these concepts really, really briefly, but I think they're important to keep in mind because they really inform where research is going and how a lot of these ideas I just mentioned, in fact, need to be qualified. I've used this example before where we have stimulation, we have a certain milliamp, we have a certain millisecond of pulse duration. We could talk about timing, burst, kilohertz, and that leads to a certain volume of tissue activated. So the full description of dose leads us to a notion of what volume is activated. But what if the cells are not all the same? What if there's one type of cell and another type of cell? And what if the threshold to activate each one of those cells is dissimilar? What if one cell type is really easy to activate and another cell type is very hard to activate? So now we can't just think about neuron. There's not just one neuron. We really have many types of neurons, and we also have non-neuronal cells like endothelial cells and glial cells, and we have compartments like a long axon that is just running along by itself, and the soma is like really somewhere far away. And so we really need to think about cell types, compartment types, and we could have a situation where the cells that are activated are actually farther away from the electrodes than other cells. So if cell type 1 is super sensitive and cell type 2 is not, we could actually have a situation where, as we're adjusting our dose parameters, the cell type 1s are firing even though they're farther away. And so there's a lot of work on designing dose, thinking about specific cell types. So you can't be cell type agnostic when you're designing dose. Okay, so then going back to this example, as I mentioned before, there are no little action potentials, right? If you stimulate, wherever you produce action potentials, you will, and where you don't produce action potentials, you won't. But you can still change cells without producing action potentials. If you polarize a cell from -70 to -60, maybe you didn't make it fire an action potential, but you sure made it easier for it to fire an action potential for another reason. What if a cell, for some reason, went from -70, right, to -51? So it's 1 millivolt away from firing. But now you apply a tiny, tiny field. Guess what? That tiny bit is enough to send it over the edge. What about polarization of dendrites? What about polarization of glial cells or endothelial cells, right, which don't even fire action potentials? those cells can still be affected. And so all this falls into this category of loosely subthreshold neuromodulation. And I need to mention it because it's very different, because now what do we mean by volume of tissue activated? We're not generating action potentials anymore as a principle. We're more modulating membrane potentials, right? And so people will talk about this is a region now where I've modulated its activity, but not necessarily made it fire. And again, this is a big area in itself, but it's a concept that needs to be kept in mind, because everything I've talked about so far was about modulation. And as I already mentioned, one thing that might make neurons much more sensitive than other neurons is if they're already active. So let's imagine that the blue ones, right, are at minus 51 millivolt. And the gray ones are at minus 70. Now we apply stimulation. Who's going to fire an action potential? It's quite likely that the blue ones will generate an action potential. Those cells were already active for some other reason. Like what reason? I don't know, the person was thinking something, or they're the cells that govern depression and they're too active in this person, right? Or there's oscillations going on that are recruiting these cells. So the cells that are already active based on background brain activity now become much more sensitive. And this sort of relates both concept that I mentioned before. Now, these three things that change everything, I don't think they're like fringe cases. I think they're actually universal, and they really need to absolutely underpin our thinking all the time. Cell type targeting, the fact that all cells are not equal and some cells are preferentially, that's a universal idea that we must be aware of. Subthreshold modulation, that it's not always about generating action potentials, that has to be in play across all forms of neuromodulation. Even the type of neuromodulation that is not called subthreshold, it's at play. And then state-dependent stimulation must be a factor for, I think, just the kind of intuition that I've given you. All right, so this concludes my hopefully simple introduction to terminology and related technical concepts that is used in neuromodulation. Thanks.